who's going to introduce our speaker for today.
Okay, so welcome Rémi. So he will present on practical advances in complex root clustering.
Thank you, Alexei, and thank you for being here. So I will present some ongoing and collaborative work with Victor, Marc Pouget, that is in Nancy, Unchi, and it's about computing clusters of complex roots, of univariate polynomials, and square triangular system of polynomial equations. So to explain what I mean by computing cluster of roots, let's consider this simple example. There are two equations involving two unknowns z1 and z2. Sigma here is a parameter, it's a positive number. And this system has 6 real solutions that are all real, A1 to A6, and here I represented the real plane. Well, when sigma grows, these roots form two sets of very close solutions that are clusters of solutions, and we want to compute polydisc that are vectors of complex disk containing the set of solutions. So here, for instance, we would like to find this polydisc delta 1, this polydisc delta 2, and report that the number of solutions in those disks, and report the number of solutions. So it may happen that...
Would you move a little slower so I can read the slides?
Sure. So here, all the solutions have multiplicity 1, and we want to find polydisc containing the set of solutions and report the number of solutions in each disk.
That may not
So I said it's a vector of complex disk. A polydisc is a vector of complex disk. So here, these rectangles are the projection on the real planes of a vector of two complex disks.
I don't understand.
So you see what is a disk in the complex plane. You take two such disks. It's a vector of complex disk, and we call this a polydisc.
Okay.
Oh, sorry.
Vector of, okay.
Vector, yeah.
And so you have 2 to the sigma. Why do you do that?
Well, so this is a parameter, and we can grow this parameter, and the solutions will be closer and closer. So you see, for instance, this solution, it has position 2 to the minus sigma 0. This one is at minus 2 to the minus sigma 0. So when sigma grows, those two solutions are closer and closer, and the same for these ones.
So but you could replace just 2 to the sigma with something else, some other number. So there's no real need to do 2 to the sigma, right?
Yeah, it's just to show that we can obtain very close roots with just this simple parameter. Yeah? You can replace sigma by something else. Okay.
I think what he wants, like he's saying, is instead of 2 to the minus sigma, why don't you just call it sigma?
Okay.
So it can happen that the solution have multiplicity greater than 1. So for instance, here when I add the squares in the system, I obtain these multiplicities for the solutions. And to handle this, now we want to report the number of solutions counted with multiplicities in each disk. So for instance, for this disk, we want to report that there are 9 solutions counted with multiplicity. So let me make...
I don't finish reading.
Yeah, it's not easy to understand this if you see it for the first time.
Okay, so
there's a way to make it easier to understand.
Okay, I've got solutions, they have multiplicities, I group them by sets that are clusters.
What is this natural clusters and then 9 and 3?
So I will, so here 9 is the number of solutions counted with multiplicities in the disk delta 1. And I will explain a bit later what means natural.
And overall, what are you trying to do? You're trying to explain what the question is? Is that what's going on, or what's going on?
So I'm just trying to explain what we mean by we want to compute cluster of solution, we want to compute polydisc that contain some closed solutions.
So you want to explain what questions you answer by giving an example?
Yeah, exactly. Yeah. And now I will give just a definition a bit more formal of what we want to do. So we want to solve what we call the local solution clustering problem, or LCP. So generally speaking, we consider a system of n equations in n unknowns, and we suppose that the set of solutions is zero-dimensional. We consider an initial region of interest in the complex space that is a polybox, and a polybox is a vector of square complex boxes. And we consider a positive epsilon, and we want to compute a set of pairs delta j and j, where the delta j's are pairwise adjoint polydisc with radius less than epsilon. We want the mj to be the sum of the number of solutions contained with multiplicities in each delta j. And we want that each solution in the initial region of interest is to be in a delta j. Well, we also only want the solutions that are in B or in a small inflation of B. This is here, delta B. This is why we call our problem local.
1 plus delta B. Presumably delta is arbitrarily small. 1 plus delta B.
Well, delta will be, yeah, maybe this is I was meaning something that is a bit more than 1.
Yeah, but
yeah,
it's a small delta
so
there.
this is, I'm sorry, this is a mistake.
So in the second bullet, is Z missing? It's the second bullet. Is it correct? Or what's this? Z is missing, right?
In the second bullet, this number means number of solutions contained with multiplicity. And I will explain this in a few minutes. So we only want the solutions that are in a small inflation of B. This is why we call our problem local. And we also want that in each polydisc delta J, when we multiply the radius by 3, we do not catch new solution. And this is to report a natural cluster structure of the solution.
What's the meaning for a small delta?
So here actually it's a small mistake, it should be 1 plus delta, and it means that we inflate a bit B.
I mean from the point of, from just so that I can read the logically.
Yeah. So logically, we want all the solutions that are in delta, and we accept solutions that are a bit outside of delta.
So is delta part of the input?
It can be part of the input.
Is it?
It can be, but actually it's fixed. So you can replace this delta by 1.1, and this is it.
I would just use epsilon since I already have epsilon, so that's 1 plus epsilon.
Okay, it should be 1, could be 1 plus epsilon. Okay, so pairs delta J where, pairs delta M where M is greater than 1 and is equal to the number of solutions in delta N in 3 delta are called natural clusters. And when the radius of delta is less than epsilon, it is a natural epsilon cluster. So in my example, those two pairs are natural clusters.
And those which call and the deltas they don't have to contain B, correct?
The deltas they don't have to. So B is if we set up this problem in the univariate case, B is a box in the complex plane, and the deltas are small, let's say small complex disks that are in B, but actually they will be in a small inflation of B.
Can you use the whiteboard to draw some pictures? I think people grasp it instantly.
So let's say that you have your initial box, your initial region of interest, and you will compute some small disk delta that are in B and that contain the solution in B. Okay? And the small inflation of B will be something like this. So those are natural clusters. And for instance, those are not, because if you increase the radius of this polydisc, you will catch new solution. So why doing root clustering instead of root isolation? So in root isolation, one wants to compute polydisc containing only one solution. So this requires to separate the solutions. So
Going back again to the slide with the deltas, the other one, the one before.
So I think people understand this plus delta thing much better if you explain what's the motivation, why we have to do that.
Yeah, this is not really the point of my talk. So
No.
But
If you want to understand why you define this problem, we have to be motivated to understand
so
why you want
the
this
point
problem.
is that if there are solutions on the boundary or very close to the boundary, it will be very difficult. I mean, it will be impossible to say if the solution is inside or outside the box. So if we allow to have two, if we allow to find solutions that are in this box but also in a small inflation, this makes the problem simpler.
It's not possible to solve it otherwise.
Okay.
Not in this model of computation.
So, yeah, in root isolation, we want to report disk containing only one solution, and this requires to separate the solutions, and for this to have input polynomials that have let's say integer coefficients, so that we can use separation bounds for distinct solutions, or at least to have the assumption that the input polynomials are square free. Because root isolation somehow requires to decide 0, but root clustering is a soft version, let's say a soft version of root isolation, because it does not require to decide 0, and it can accept input polynomial, which coefficients are any complex number, even algebraic numbers, and this is also robust to multiple roots.
Real question. Could you explain OR? So the first two bullets are separated by OR.
Yeah, so when you do root isolation, if you have as an assumption that the polynomial is square free, you can, you can do root isolation even if you don't have the root separation, even if you don't know exactly the coefficients. If you have the assumption that there are only simple roots.
And by square free, and so are you doing this to a single polynomial or to a system?
So here it will be for a system.
But then square free does not imply that the ideal is radical. If just every polynomial is square free. You must still have multiplicity. It's not a problem?
It will be a problem. So
I missed that all when downstairs picked up pen. He said that he's come to the seminar but he can't get it.
Oh, Victor Pan is down there, yeah, get it.
When time goes over, I have my end.
Okay, thank you.
So we place curve free with only simple solutions. Solution with no multiplicity.
No multiplicity.
Yeah.
Do you know why? Why square free helps you even in the univariate case?
If you want to separate the roots.
In other
If you want
words,
to do
as long
root
as you have
isolation.
more than one root, you keep refining it.
Yeah. Okay, so this talk begins with the fact that
Maybe.
menu, yeah, this is the aperitif.
And
So-
I get to choose, or who gets to choose? Who gets to choose?
Oh, there is no choice.
Choose.
So the talk begins with the fact that the local clustering problem for the univariate case has been solved with an algorithm proposed in this paper, and it's been solved in a near optimal way, meaning that the bit complexity is is close to the best one could expect for polynomials with integer coefficients. And this algorithm has been efficiently implemented, and it's described in this paper, and it's available to the community. And later I will refer to this implementation by Ccluster. So I will first present some basic tools used in this algorithm in order to be able to embed them in an algorithm for solving the LCP for solving triangular systems of equations. And by triangular, I mean that the first equation involves only one unknown z1, the second one involves two unknowns z1, z2, etc. So solving this kind of system is intuitively quite simple, because if we find the roots of f1, for each root, in each root we can specialize f2, and then we obtain a multivariate polynomial. In each root of f1 we specialize f2 to obtain a univariate polynomial, and we can find its roots. But in practice, this requires to find the roots of a polynomial which coefficients are in extension field. And for this, the tools from clustering, for complex clustering, are particularly appropriated. So why considering this
And here,
kind?
So are there any assumptions for square free here?
So here actually with the method I will present, we don't have this assumption. So the assumption we have is that it has a finite number of solutions.
It has to be regular.
So why considering this kind of systems? Okay, this triangular system appears when we do symbolic numeric solving for general system of polynomials. So we can transform a non-triangular system with some symbolic tools in a triangular system. So this is this rewriting step. So it could be transformed in one triangular system or in a set of triangular systems. And then maybe one wants to find the roots of this system.
But when you do the transformation, don't you also get inequations? Like something not equal to zero? Or like some components?
I guess that in the methods that do the rewriting, they will manage these cases by doing several systems of several triangular systems, by
So several
putting several
triangular
triangular systems.
And each of them is not just so it's just set of equations in the same variables without inequations.
Yeah, without inequations.
Really?
Well, for instance, with regular chains.
Yeah, you're getting inequations there.
Well,
Right, that's triangular sets, right? Solving like characteristic sets.
Yes, yes.
There'll be something
Not
outside of.
Yeah, yeah. So
Yeah.
you're supposed to get inequations here as well. When you do, I guess if you want to restrict just to
Triangular sets,
So-
but I guess you can maybe do other things other than triangular sets. I think you
if
can.
you want to guarantee that it's of this exactly of this shape.
Can't you always get them to regular sets without inequations?
If you introduce an extra variable, then you can get rid of the inequation. But he uses the same variables.
Well, this
Well,
is the
they-
motivation
they-
and
yeah.
um,
I'm a bit surprised, but I will check. But with the tools I used to make some experiments, for instance, with regular chain, we just obtained a set of systems with no inequation.
no, that you are taking from somebody's system.
Yeah.
Yeah,
Yeah.
but
Yeah,
But
some
in
examples.
general, Alexei is talking about the problem transforming from
Yeah.
that step to that one, and one way is using characteristic sets,
Yeah.
right? Characteristic sets will have inequations.
Computer limited for the giving system always can.
Can do it without
Yeah,
inequations, I think. Right.
It can form the triangular system.
But would it be regular?
Triangular, I'm not sure about this.
Yeah, they may have other defects in the system, not quite sure.
Well, so actually, our motivation is to solve this kind of triangular system with no inequation. But we have the assumption that there is a finite number of solutions. So instead of doing a state-of-the-art of what exists, to do so, I propose to do just a small experiment. I consider two systems of three equations in three unknowns, S4 and S5. So the leading monomials of S4 has degree 4 and the ones of S5 have degree 5, and I use two symbolic numeric approaches to solve this system. First, with the function isolate RC, so with regular chain of maple, and I separate the time for the symbolic step and the time for solving the triangular system. So I'm calling this step numeric. And with regular chain, Maple has a solver that finds the real solutions, and it seems that it's more difficult to find the real solution of the triangular system than to apply the symbolic step. So actually it should not be the case, because there exists some very good solver for the real case that should be way faster than this. But in any case, we can also use the solve.lib library from Singular. So here the symbolic step is performed by computing Grobner bases. And then there is a solver that finds all the complex solutions, so it's very fast, but there is no guarantee on the precision of the output. So with the algorithm I will present, will be called Ccluster, and we also can compute all the complex solutions with less running times, but we have a guarantee on the output. Okay, so then after the multivariate triangular case, I will come back to the univariate case and propose two improvements. Okay, so let's give an outline on the basic tools for the univariate case. So for this, let me introduce some concepts on numbers I consider. So for a complex number alpha, I call an oracle for alpha a function that maps to an integer, an interval that contains a complex interval that contains alpha and has width less than 2 to the minus n. Then an oracle for a polynomial is the given of oracles for its coefficients, but it can also be seen as a function that maps to an integer L, an interval polynomial, and this interval polynomial will contain the initial polynomial f. Alexa, you have questions?
I'm just trying to read this. I've never seen this notation before, so I just.
Okay. So that's why I'm explaining the notations.
Takes time to.
Yeah. So now, not new notation. Let me outline algorithm for the univariate case. So we consider two tests. We suppose that we have two tests. A test for counting the number of solutions in a complex disk. So the complex disk will be here delta. The test is called T star. And for a given complex disk and an oracle for a polynomial, it will return an integer that is either positive, in which case it means that f has exactly this number of roots in delta, or -1 when the test fails, because this test can fail. Then we have a discarding test, T0, for a complex disk that can return either 0, and it means that the polynomial has no root in the disk delta, or -1 because the test can also fail. And then we interleave these two tests in a subdivision approach. So for the initial region of interest B, we have a list of subboxes that may contain roots. We first quadrisect each subbox, and then for each subbox we apply the discarding test in a containing disk of the box. So eventually we will discard some boxes, and then we group the remaining boxes into connected components, and we apply the counting test on a containing disk of the connected component. And if the counting test succeeds and returns a number of roots, and if 3 times this containing disk do not intersect other remaining subboxes, then we have a natural cluster.
And do clusters have to be connected?
Sorry?
Are your clusters always connected?
The clusters are...
Connected. Are they
So
always
here the clusters are represented by a set of subboxes, by a connected component of subboxes.
Yeah, but in general, do your clusters have to be connected?
But the cluster is a set of isolated points.
No, okay, so I meant, I thought the cluster was the region that you know, your deltas.
So the cluster is a set.
I think you defined it as deltas, right? Delta. And delta is a...
So the cluster is a set of solution.
It's a polydisk.
Yes, you define cluster as a delta.
And what we call a cluster.
Are the roots in a polydisk. There exists a polydisk that contains it. Those are called clusters of roots.
Okay, so this discarding test can be implemented with the counting test. So this counting test is the heart of the method. And on the clustering univariate algorithm, it's based on Pellet theorem. So for an initial complex disk delta centered in C with values R, we defined f delta as f evaluated in C plus RZ. So it's the shift and scale of f on delta. And the Pellet theorem states that if there is an integer m so that the m's coefficient in absolute value is greater than the sum of all other coefficients, then f has exactly m roots counted with multiplicity in the disk. And one can show that if there is no root in this annulus around the contour of delta, and the size of this annulus is a function of the radius of delta r, then there will exist an integer m so that one of these inequalities hold. So this theorem will allow to decide the number of roots in the disk. So to reduce the size of this annulus, one can use, for instance, Dunning-Greffer iterations. But here, I consider a simple version of this theorem, and I derive from this theorem a test. So that takes input a complex disk, delta, and a polynomial. We first compute f delta, and then for each index corresponding to coefficients, we try to check if this inequality holds. If it does, we return the index m, and it means that there are m roots counted with multiplicity in the disk. And if there is no m so that this inequality holds, we return -1. And it will mean that there are roots near the boundary of delta. Well, now this is for a polynomial that is known exactly, but we want to do this first for interval polynomials. So we need to decide this inequality when the coefficients of the polynomials are intervals. And so for this, we introduce a function for comparing real intervals, box A and box B. So this soft comparison will return 1 when box A is greater than box B, -1, meaning that any points in A is greater than any points in B, -1 if any point in A is less than any points in B, or if the two intervals intersect and the bounds are too close, and otherwise it will return -2. So we can embed this soft comparison into what we call a soft Pellet test. So it's for interval polynomials. We first compute box f delta, that is an interval polynomial, and then for each index of coefficient, we try to decide if the inequality holds with the soft comparison function. So if it returns a positive number, it means that any polynomial in box f, the interval polynomial, has m root counted with multiplicity. If it returns -2, it means that the polynomial box f is too wide to be able to decide one of the inequalities. And if none of this holds for all coefficients m, we return -1. It means that there are roots near the boundary. So now if we want to define the same thing for oracle polynomials, that are polynomials for which we can have as much precision as we want on the coefficients, we can just embed this test on a loop where the precision is increased. So we get a first interval polynomial for the oracle, we call the soft Pellet test, and while it returns -2, we increase the precision and ask more precision on the coefficients of f. Okay, so this gives a clustering procedure that I call cluster oracle. That is exactly the one that is described in this paper. So it uses this T-star test for oracle polynomials. But I will need to consider an alternative version of this procedure that is called cluster interval that use the soft Pellet test for interval polynomials. So it takes as input an interval polynomial and applies the soft Pellet test. And when one of the soft Pellet tests returns -2, we say that this procedure fails and it returns fail. Otherwise, it succeeds and it will return a list of natural clusters that solve the LCP. All right, so we are now armed for the multivariate triangular case. To simplify, I will consider only the bivariate case, and I will suppose that the polynomials of the system of equations have rational coefficients. So the first equations, the polynomial is f1, it involves z1. The second one is f2, it involves z1, z2. And let me introduce a new definition. For a polynomial f2, a bivariate polynomial and a complex number alpha 1, I call the partial specialization of f2 in alpha 1 the univariate polynomial obtained by replacing each occurrence of z1 by alpha 1. So this is an interval with complex coefficient. And I can do the same when alpha 1 is an interval, complex interval. So I replace each occurrence of z1 by box alpha 1, and I obtain a polynomial which coefficients are interval.
And can
So-
it happen that if you substitute one of the roots of f1 in f2, f2 becomes 0?
So this is actually if f2 becomes 0, it will mean that the system has an infinite number of solutions.
Can it happen that the degree will drop?
Yeah, the degree. Yeah, it can happen that the degree decreases, and it means that there are some solutions that goes to infinity. But we cannot have a polynomial that is identically 0 when we substitute with a root, otherwise it means that the system has an infinite number of solutions. All right, so what we need is a way of counting the number of solutions in a polydisc. So here the polydisc is delta 1, delta 2. So to do so, suppose that the polydisc is such that delta 1 contains m1 roots with multiplicity of f1, and then for each root of f1 in delta 1, f2 specialized in alpha 1 has exactly m2 roots in delta 2 counted with multiplicity. So then, under that condition, we can deduce that there are m2 times m1 solutions in delta counted with multiplicity. And this is actually a direct consequence of this theorem coming from this paper that states that for a triangular system, so it's for triangular system. For a triangular system, the multiplicity of a root is equal to the product of the multiplicities in the fibers. So back to my initial example, to obtain these multiplicities of the roots, I actually applied the theorem.
Would you
So this theorem states that f is a triangular system, alpha is a root of f, its components are alpha 1, alpha 2, and the multiplicity of alpha as a solution of f is equal to the multiplicity of alpha 1 as a solution of f1 times the multiplicity of alpha 2 as a solution of f2 specialized in f1, in alpha 1. So to obtain those multiplicities, I applied this theorem. And if I apply my proposition 1 that was on the previous slide, I can decompose this number 9 into a product of multiplicities in the fibers.
How do you define multiplicity over root?
So there is basically two kinds of definitions. One that uses localization in rings, but it's quite involved. So this is the algebraic definition. And there is one coming from differential calculus that will correspond to the dimension of linear space, and it will be of the linear space of differential functions that vanish on the ideal. So it's kind of involved. But for triangular systems,
we don't compute the multiplicity error, we compute the total multiplicity in the disk. So if you have a single root with multiplicity, yes, you will get that as well. But if you have 5 roots, you sum up all the multiplicity, and that's what you get. The Pellet test will give that.
But you are asking how we define the multiplicity.
Yeah, the definition,
The definition, so in the general case, the definition is quite involved, but for the triangular case, we can at least compute the multiplicity, or since it is equivalent, we can define the multiplicity of this number. And the two definitions will be equivalent. Okay, so let me go ahead. So I introduce a definition I call natural tower a pair delta m, where delta 1 m1 is a natural cluster relative to f. So delta 1 contains m1 roots of f1. And then for any points in delta 1, delta 2 m2 is a natural cluster relative to f2 of alpha. So actually, this second condition for being a natural tower is a bit stronger than the second condition for this proposition. So if a pair is a natural tower, it will satisfy this proposition, and we can count the number of roots with multiplicity that will be m2 times m1. And when the radius of delta of the two components is less than epsilon, we say that this is an epsilon tower. So in my example, the natural towers that correspond to the natural clusters are these pairs, delta 1, 3, 3, and delta 2, 1, 3. Well, now this is the same definition than previously, the one of natural tower. And actually, this definition, I mean, the requirement to be a natural tower, has been shaped so that we can verify it with the Pellet test. So suppose that the soft Pellet test with input delta 1 m1, f1 returns m1, and then the soft Pellet test with input delta 2 and f2 specialized in the interval containing delta 1 returns m2, then this pair delta m will be a natural tower relative to f, and we will be able to count the solution that are in delta. So this is just to explain what I mean by interval containing a disk. Well, now actually, I'm ready to present the main algorithm that will use a data structure, and mainly it will use this data structure, that is a tower. What we call a tower is a triple, L, B, capital L. L will be called the level, and I will explain what it is later. B is the domain of the tower, so it's a polybox. And L, capital L, is a vector of integers L1, L2 called precision. So what we will do with these towers, we will guarantee that when the level is equal to 1, there will exist a number m1, an integer m1, so that the soft Pellet test with this input, so the containing disk of B1 and F1 returns M1, and the radius of this disk is less than 2 to the minus L1, so the first element of the precision. And when the level is 2, we'll guarantee that there are two integers, M1, M2, so that the first condition holds, and the soft Pellet test for inputs containing disk of B2 and F2 specialized in the containing interval of containing disk of B1 returns M2, and the radius of the containing disk of B2 is less than 2 to the minus L2, that is the second precision. And if this holds, then there are M2 times M1 solution in B, or in delta B. Okay, so what we will do with these towers is to lift them. So if a tower has level 0, we want to lift it to level 1. So for this, we can apply our function cluster oracle. So we have an oracle for polynomial f1, and the region of interest will be b1, and the size 2 to the minus L1. So this will apply a subdivision in the first component of the box, b1, and return a list of natural clusters that solve the LCP for F1. And from this list, we form towers at level 1 by appending B2 at the second component. Well, now to lift a tower from level 1 to level 2, we can use our function cluster interval. So the input interval polynomial will be F2 specialized in the containing box of the containing disk of B1. The region of interest will be B2, the precision 2 to the minus L2. So recall that this function cluster interval can fail if this polynomial is not precise enough. So it will mean that B1 is not small enough. So if it fails, we need to refine B1. Well, now, this is our main algorithm. So we have an input, a triangular system, an initial domain B, and a precision L, capital L. And we want to output a set of 2 to the minus L towers that solve the LCP. So we form a first tower at level 0 with domain B and vector of precision LL. And then we push this tower in a queue, and while this queue contains towers at level less than 2, we pop such a tower, and then if the level is 0, then we lift it at level 1 with our function cluster1. And if the level is 2, we try to lift it at level 2 with our function cluster2. So if this call succeeds, then we push the results in the queue, and otherwise, if it fails, it means that we have to refine the first component of the tower. So we do it by defining a tower at level 0 with the same domain, but we double the ask precision for the first component, and we push it in queue. All right, so this is it was our algorithm. So we implemented it. So the base for this implementation is the univariate clustering algorithm called Ccluster. So this is a C library, but there is also an interface for Julia called ccluster.gl. And we implemented Ccluster in this interface for Julia. So the algorithm is implemented in Julia. And I will just give some results. So here I considered randomly generated triangular systems with a number of equations growing and increasing degree. And first for each system, so some systems with only with simple solutions and some systems with multiple solutions. And first I applied two versions of Ccluster. A local version, so the region of interest is a small box that will contain only a small number of solutions. And a global version, so actually we set the box with an upper bound for roots of polynomials. And so the initial box will contain all the roots of the systems. So, and here are the running time. So our algorithm is way more efficient locally than when all the roots have to be computed. So now, for external comparison, I compare with an homotopy solver that is also implemented in Julia.
Can you focus on one line? Just focus on one line. Tell us what.
So here, what is important will be just the times. Okay. And compare this column.
All times look great.
Hmm?
The times look great. They all look great.
Yeah, they are great. I just present great times. The ones that are not good, I don't present it.
Okay.
No,
No, honestly.
No,
I
this
mean,
is a-
what,
no,
you
no.
have other times which are not great.
well, this was somehow a joke, but
Yeah, I know, but no, I'm serious. I mean,
No, no.
I always believe we should present things that make us look better.
no, seriously, I already presented in the introduction the comparison with the solver of Singular that is very fast and that beats
Us.
that beats us.
In all these examples.
No, not on these examples, but on examples that come from symbolic numeric solving, it beats us.
But does it
Here-
output the same thing?
Actually, here, so there are triangular systems, and for instance, here in the first line, the first equation has degree 9, the second has degree 9, the third has degree 9. When you use a symbolic method to triangularize a system, the shape will be quite different. In general, the first equation will have a very high degree, and the other equations will have degree 1. So the shape will be quite different.
I don't understand. So when you do random
Triangular,
triangular, and how do you arrange random with multiple solutions?
well, we just,
What is random there when you do random?
so actually we compute random solution and then we take the square, random polynomials and then we take the square of the polynomial and it will generate solutions with multiplicity.
Okay.
And so the
So
coefficients
that part is
are,
not random.
Hmm?
That part, wait,
it's random with the structure. Okay, so for an external comparison with an homotopy solver, homotopy continuation.gl. So with this solver, I solve the triangular system, but homotopy is way more general than what we do. But I just use it to solve the general system. So the running times are quite similar, but we are way faster for systems with multiple solutions just because homotopy solver has to track a number of paths that is equal to the Bezout bound of the system.
So they lose path, right? They don't get all the paths.
Oh, actually, so they lose some paths and also they fail in deciding multiplicities for solution. So yeah, here they do not compute the exact number of solutions. Okay, and
do they,
then
do they answer the same question?
can you say it again?
So you're comparing algorithms.
Yeah.
But these algorithms answer different questions, correct?
So yeah, they answer quite different questions.
So could you explain the point of comparing algorithms that answer different questions?
So homotopy will find all the complex solutions, right? Okay, that is what we will do, but we group the solutions in clusters.
Is it better to have them grouped in
It's
clusters?
different. It's different because somehow this is more general because we are robust to multiplicities and we can accept polynomials that are not known exactly. But there are something that we cannot do. For instance, deciding realness of a solution, deciding separating the solution, we cannot do it. So this is more general, but there's something we cannot do. Okay, so I don't say that this comparison is a good comparison. We just need to do comparisons. Okay.
And this triangle.
And the last one is the numeric solver in the solve.lib in Singular. So that performs very well for systems coming from a triangular symbolic step. But for the kind of system we try, actually the solving time are quite similar with our solving times. except for very big systems.
But they're all great. So like choose whatever result you get.
Well, we give a guarantee on the output.
What do they
Something else.
guarantee? What method does Singular use?
The problem is that the method is not documented at all. So to understand what they do, you have to open the code and to read the code. So hopefully it's written in Singular language and not in C. But if you want to know what they do, you have to read the code of the library. So
Okay, that's funny.
that's funny, but yeah.
But there is no manual that says that's what the output is.
It's really poorly specified.
Okay.
Yeah. So there is paper that is cited for the symbolic step, but not for the numeric step.
Yeah, usually these numeric steps are very flaky. Even Maple's numeric steps are very flaky.
So let's continue. So
Where's the dessert menu?
dessert, I mean, this would be the true normal. You know what it is? It's the ice cream between the two.
Okay.
Yeah. So now it's the true normal, and then it's another plate. So the first improvement in the univariate case is for polynomials with real coefficient, and it's a very practical improvement. So this kind of polynomial have roots that are either real or come in complex conjugated pairs. So we propose to leverage on this geometric property for subdivision algorithms. The idea is to consider the part of the complex plane that is above the real line. So in the subdivision tree, we only consider boxes that are above the real line or contain the real line. And it allows to reduce the number of discarding tests that are performed in the clustering algorithm. And the less the number of real roots a polynomial have, the more important will be this improvement. So for instance, with a miniot polynomial with degree d, so when d equals 64, the roots are drawn here. When d is even, it has only 4 roots. And here I draw the subdivision trees without the improvement and with the improvement.
Why do you, in the improvement, why do you go above the real line?
I go only above the real line,
Yeah, but
and I deduce the
as long
roots.
as any box does not contain the real line, you don't want it, right?
No, we want all the roots.
Oh, you do want all.
Yeah, maybe it's not clear.
Sorry.
I'm doing clustering complex roots for polynomials with
Okay.
real coefficients. Yeah.
I thought you were doing real.
No, I don't know yet how to do it. So it allows to reduce the number of discarding tests we do. So for instance, with this polynomial that has only 4 roots, without the improvement, we do this number of discarding tests, and with the improvement, we do about half of this number. So it's a bit less interesting for polynomials, for instance, the Bernoulli polynomials that have a lot of real roots. So here, this polynomial, when d is even, has a quarter of the real roots. So here are again the subdivision trees and the number of discarding tests. So here we do the ratio, both by the improvement is 0.6, so it's a bit less interesting than for miniot polynomials, but it still works. So here are timings for this improvement. So for miniot polynomials, so Ccluster is the original clustering algorithm, and Ccluster R is the same algorithm but with the improvements for real polynomials. So for miniot polynomials, these lines, we about halve the running time. And for Bernoulli polynomials, it's a bit less, but it's interesting. Okay, so a more significant contribution is about a new test for counting the number of solutions in the number of roots in a complex disk. So this counting test comes from a theory that is made to approximate power sums of roots in disk. So to simplify here, I consider delta, that is the unit disk. And let's say that in this disk, the roots are alpha 1, etc. to alpha d delta. So there are d delta roots with these multiplicities. So for an integer h, the h's power sum is the sum of the h powers of the roots weighted by the multiplicities. And there is a theorem that says that provided that the disk is row isolated, and this means that the roots that are inside the disk have modulus less than 1 by row, and the roots that are outside the disk have modulus more than row. So provided that this disk is row isolating, defining an integer q, and we can use evaluations of f and its derivative at q points to approximate the h power sum with an error that decreases about as d times rho to the minus q. So actually what we want here is just to count the number of roots, and the number of roots is actually the zeroth power sum. So let's specialize this just for the zeroth power sum. Okay, so for an integer q, we define this number S0 star that involves the evaluations of the polynomial and its derivative at the q's roots of unity that are drawn here for q equals 8. Okay, so now, as a consequence of the theorem I was citing previously, provided that the disk is row isolating and defining theta as 1 divided by rho, we can say that the distance of S0 star to the number of roots is less than this number, that is about d times theta to the q. And now, if we are given an error to which we want to approximate the number of roots, delta, we can deduce the number of points on which we have to evaluate the polynomials with this formula, and we obtain a S0 star that approximates 0 with an error less than delta. And since S0 we want to approximate is an integer, it suffices to take delta less than, let's say, a quarter. So if this delta is less than a quarter, the disk of radius a quarter around S0 star will contain a unique integer, and this integer will be the number of roots. Okay, in order to define formally our test, I just need a new definition, what I call the evaluation oracle for a polynomial f. So this is a function that maps to an integer and an oracle for a number alpha, a complex interval, so that f, the evaluation of f in alpha is contained in the interval, and the width of the interval is less than 2 to the minus n. Well, and now this is our p-star test. So for input, the complex disk delta, the isolation ratio, rho, and evaluation oracles for f and its derivative, we first choose an error delta that is a quarter, and then we deduce from this formula the number of points on which we have to evaluate our polynomial. Then we use q and our evaluation oracles to obtain an interval containing S0 star with a width less than a half. And then since we know that any point in S0 star is, no, that the number S0 we want is at a distance less than a quarter of at least a point in S0 star, we enlarge this interval of this with this ratio, and we obtain box S0 that has width less than 1 and that contains a unique integer. And this unique integer is the number of roots in the disk. So for example, if f has degree 500 and the disk is too isolating, it suffices to evaluate f and its derivative f prime at 11 points. Then to compute S0, we have to do a number of operations that has the same order than Q. So the efficiency of this test is directly related to efficiency of evaluation. So the faster will be the evaluation, the faster this test will work. So to illustrate this, to illustrate how efficient is this test compared to the test based on the Pellet theorem, here I run Ccluster on two Bernoulli and Mignot polynomials, and I report here in this column T0 the total time spent in doing the discarding test with the Pellet theorem. And each time I do a discarding test with the Pellet theorem, I also do it with the P-star test. And I report here, so let's forget about this for now. I report here the time spent in the test. So in both cases, the improvement is, in terms of time, is very interesting. But in particular for Mignot polynomial, this is actually because Mignot polynomial, let me just show again its definition, I'm sorry for this. So Mignot polynomial actually is very sparse, it has only 4 non-zero coefficients, so it can be evaluated very fast. Well, but the problem is that this test requires the isolation ratio rho to be known and greater than 1. So actually we cannot apply this test as a discarding test, and here I was cheating. What I was doing is applying the test with an arbitrary isolation ratio of 2. So in this case, if 2 is not the actual isolation ratio, S0 can either contain no integer or contain an integer that is wrong and that is not the correct number. So here I report the number of time S0 was not containing any integer, and here the number of times this integer was not the number of solution. So actually, even if we don't know the isolation ratio and we choose a number arbitrarily, it is very likely that it returns the appropriated number of solutions. So we would like to use this fact, to embed this in an algorithm, so we don't know exactly how yet.
How much would it speed up the algorithm?
So if we were able to only use this test instead of the Pellet test, we will go from 27 seconds to 0.6 seconds. But it's not possible, because, now we don't know how to do it. Yeah. So what we propose, but is to use this P-star test as a filter. So when we want to discard a disk, we call the P-star test with an isolation ratio of 2, even if we don't know if it's true. And when it returns 0, we confirm this number with the Pellet test. And let's give some times about using this P-star test as a filter. So the version of Ccluster that uses this is Ccluster P. And this is the improvement in terms of running time that is allowed by this P-star test as a filter. So it's quite interesting for minute polynomials, but not that much for Bernoulli. So again, actually the slides was here. It's because minute polynomials can be evaluated very fast because it's sparse. So other kind of polynomials that can be evaluated very fast are polynomials that are defined by a procedure. So for instance, the Mandelbrot polynomial is defined by this recursive procedure. So when we do 6 recursion, we obtain a polynomial of degree 63, which roots are here. Another example is the Ronald polynomial. The recursive formula is here, the recursive procedure is here. When doing 8 recursion, we have a polynomial of degree 117, and the roots are here. So these polynomials can be evaluated very fast because we just have to apply the procedure. So for these polynomials, our Ccluster P brings this improvement compared to Ccluster real. So overall, with the 2 improvements, this is the real time of the initial version, and this is the running time of the new version. And just before I finish, because I gave a lot of running time for the clustering algorithm and some improvement, just to put it in the context, how perform the other method. And I just propose to give the running time of MP-solve that also finds all the complex roots, but that is based on simultaneous Newton iterations. So MP-solve will perform way, way faster than us, but we are making progress. So, we don't hope to beat MP-solve, but to be a bit closer than MP-solve. So, thank you for your attention.
Questions?
So the filter idea, well, I mean, if you don't know the isolation ratio, you can keep decreasing the ratio, right? Does it increase or decrease? Push it towards 1, right?
Yeah.
Push it towards 1. Would that will eventually give you the correct thing, unless you have 0 on the circle, on the unit circle. And
but actually, for an isolation of 1, the number of points you have to on which you have to evaluate the polynomial will be infinite. So you have to be still just a bit above 1.
Yeah, a bit above 1. And this circle, you move it around, right? It's not always in the circle, but you have to that transformation is expensive, isn't it? That's Taylor shift.
So here we don't need to do the Taylor shift. Yeah. So I presented the test for the unit disk, but actually instead of evaluating the polynomial on the Q's roots of unity, we can just do it in C plus R times omega, meaning that we shift and scale the roots of unity.
So the polynomial has to be transformed?
No.
You don't have to transform?
No, instead of...
you just change the argument.
I just changed the argument.
I see.
So,
okay, that's very important.
So I just, instead of evaluating on these roots of unity, I evaluate on these points.
That will allow you to test over there without
shifting the polynomial.
Right. That's very efficient.
Yeah.
Much better than the usual Taylor shift. That's great. So I suspect this can be put into a very nice tool. It's just that right now it's not there. But, Very interesting. Questions?
Nick, do you have any comments?
I think it's just the beginning. We may improve a lot. I mean, univariate case.
But by improve, you mean improve
Yeah,
what?
well, there are some directions more efficient.
You mean faster, just to do.
Faster, also the, well, it was not mentioned here, but the new counting test applies to polynomial which can be, which are given by black box for their evaluation, which is an advantage against Pellet test. Pellet test requires coefficients, but in this case we don't need.
So this is what I was mentioning with procedural polynomials. You don't need to know the coefficients of the polynomial, you have just a black box to evaluate it. And the procedure will give you the black box.
For instance, for Mandelbrot polynomials, it's important. Okay.
Questions, comments? Okay, thank you.
Yeah.